All right, team. So we are jumping into section 11.3. And as promised, this section, we're going to look more in depth at the logical implication or the conditional connective, right? So this was the double arrow, and we call this the conditional connective. This is your if and then statement. All right, so let's jump right in and look at the truth table for the conditional connective, the implication. Now, the implication is a little counterintuitive sometimes. And in order to make the truth table make more sense, I often think about it in terms of the following. If you start with a work of fact, like like an actual scientific work or something that's supposed to be strictly factual, then you are not allowed to have any fiction within the factual document. Okay. So a purely factual document should have nothing but fact in it. Vice versa, if you have a work of fiction, a fictional document, it can have fiction in it or it can have fact in it. That there is no sort of contradiction there. You can have works of fiction that have fact, but you cannot have works of fact that have fiction. And that's often how I think about this. So think of P as what type of document do you have? Do you have a document that's a factual document or a fictional document? And think of Q as something that's inside of that document. Is Q allowed to be inside such a document? So for instance, P is true. I'm going to say true is fact. So P is a factual document. Is it okay for a factual document, P, to have facts inside of it? Yes, that is okay. So a true premise implies a true conclusion. And that gives us truth. So fact inside of fact is okay. That's how I think of it. Okay. Again, P is true. Think of P as a factual document. If you have a factual document, T is what's telling me it's fact. Is it okay to have fiction inside of fact? No. A purely factual document should have no fiction. So that's false. Okay. Now P is F. So now P is a fictional document. Is it okay to have fact, T, truth is fact. Is it okay to have fact inside of fiction? Yeah, you can have fact inside of fiction. Think about it. You can have historical narratives, right? Or historical novels. The story of Abraham Lincoln. Some things have to be made up because no one knows exactly what Abraham Lincoln said here or there, right? But there's plenty of factual events within such a historical novel, like the battle or the Gettysburg Address or something like that. That would be purely fact. So you can have fact inside of fiction. That is okay. Okay. And then here's the next thing. Pause for the cause. Hold on. Sorry about that. Okay, so and this last entry in the truth table is the one that's most counterintuitive. Okay, but if you think of it in terms of fact and fiction, it'll make sense. So P is a work of fiction. Is it okay to have fiction inside of fiction? Yeah, of course. Otherwise, it wouldn't be fiction, right? So that is true. And that's very counterintuitive. You can have two falses. A false can imply a false, and you get a true statement. This makes sense intuitively in the way that if you start from a false idea and you get to a false conclusion, that kind of makes sense. You would get to a false conclusion from a false premise, and therefore you have truth. If that doesn't quite gel with you, again, think of T as representing, very loosely, fact, and think of false as fiction. And every time you can say, is it okay to have fact within a factual work? Yes. Is it okay to have fiction inside of a factual work? No. Is it okay to have fact inside of a fictional work? Yes. Is it okay to have fiction inside of a fictional work? Yes. I find that just makes sense to me. Maybe that will be helpful to you in remembering the truth values for the implication. Okay. Now, implications can be read various different ways, right? So for each of these English sentences, these are all equivalent to P arrow Q. Okay, so we could read it as P implies Q, P implies Q, or if P then Q, if P then Q, P only if Q, P only if Q, Q if P. So we can say Q if P, or P is sufficient for Q, P is sufficient for Q, or Q is a necessary condition for P. Q is necessary for P. All of these are equivalent ways of reading the implication symbols, and also ways in which you might see statements phrased. Okay, let's look at some examples. So we want to determine the truth value for the following statements. If Paris is in France, then the Louvre is in Paris. Okay, so how do we do this? What we need to do is identify the individual statements P and Q. So for us, P will be Paris is in France, and Q will be the Louvre is in Paris. Okay, let me give us a zoom in here. Right, so that this is our P and this is our Q. So this is saying if P, then Q. So what do? We evaluate the truth value of the individual statements. Is Paris in France? Yes, that's true. Is the Louvre in Paris? Yes, that's also true. So we have if P, then Q, if true, then true. So what is the ultimate truth value of this statement? Well, at first you can use your table, right? So we have if true, then true. True, then true gives us true. So the truth value for the first statement is true. Okay, let's look at another one. If 2 + 3 = 7, then the Louvre is in Paris. All right, so what are our individual statements? The first one, P, is 2 + 3 = 7. The second one, Q, is the Louvre is in Paris. Okay, so now we identify the individual truth values for these statements. Is 2 + 3 = 7? No, so that is false. Is the Louvre in Paris? Yes, that is true. So what do we have? We have false implies true. All right. So again, think about the fact and the fiction idea. If we have a work of fiction, is it okay to have facts inside of a work of fiction? Yes, that's okay. So we can start from a false idea and get to a true idea. This is still true. So remember, this is the implication can be sort of counterintuitive, but I swear, if you think about it in terms of fact and fiction, it makes more sense. Okay. So let's look at another example. We want to construct a truth table for the following statement. If the president dies or becomes incapacitated, then the vice president becomes president. Okay. So let's parse this all out. First, let's identify all the statements involved. The first statement is the president dies. That is one statement. We also have a statement, becomes incapacitated. So the president becomes incapacitated. That's a whole other simple statement. The last statement is the vice president becomes president. So those are three statements altogether. So we can give them names. P is the president dies. Q is the president becomes incapacitated. And R will be the vice president becomes the president. So those are our three statements. So we want to make a truth table for this. So we'll put down P. Hopefully I have enough room here. We'll put down Q. And we'll put down R. So we need the three simple statements. And remember how this works. How many rows will we have? We always take, to figure out the number of rows that we need, we take 2 and raise it to the power of the number of variables. So that's 2 to the 3, which is 8. So we're gonna have to have 8 rows for this truth table. And remember how we do this. We start with P and we do 4 truths and then 4 falses. Then with Q, we do 2 truths, 2 falses, repeating. This is so we can get all the combinations. And then for R, we just go true, false, all the way down. So that way we get all the various combinations of the simple statements, various truth value combinations. Okay, so let's see if we can write down this statement. What are all the connectives that we see? Well, we see an if statement and a then statement. So that's an implication, but we also see an or. So those are all the connectives involved. So if what is the premise of the conditional? If the president dies or becomes incapacitated. So that's the whole if. So everything here to there. Excuse me. So how do we write down that statement? That is P or Q. Okay. And P or Q implies who? R. So that's the translation of this statement into symbols. So now we want to evaluate the truth value for this complex statement. And I'm going to show you this is sort of a shortcut, and they show you this in the book. Instead of having to make a bunch of different columns for each special connective, we can kind of consolidate things. So the way you can visualize this is there's sort of an imaginary column here for the P or Q, and then there's another column for the implication. So this part implies R is another column. Okay, so let's write down all the truth values for P or Q. All right, so P or Q, true or true. So all we need for an or statement to be true is at least one true. So if we look down the combinations, all we need is one true, and we're true. So true, true gives us true, 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 false, false, true, false, true, false, false gives us a false, and then false, false again. So those are all of the truth values for the P or Q statement. Now we're going to do the implications. So for the implications, we are using the whole P or Q as the premise for the implication. So this complex statement becomes, we visualize it as its own statement. It is the premise of this big implication. So we're going to look at this implies that. And so in order to evaluate the truth value, we're going to look at this column and compare it to this column. And we're going to have to kind of go backwards. So does true imply true? Can we have within a work of fact, can we have fact? Yes. Okay. In a work of fact, can we have fiction? No. Okay. In a work of fact, sorry, I'm looking at the wrong, let me make sure I was doing these right. I'm supposed to be comparing these two, sorry. So true, true gives us a true. In a work of fact, can we have fiction? No. All right. In a work of fact, can we have fact? Yes. Okay, next one down. In a work of fact, what is going on here? Yeah. In a work of fact, can we have fiction? No. In a work of fact, can we have fact? Yes. In a work of fact, can we have fiction? No. In a work of fiction, can we have fact? Yes. And then finally, in a work of fiction, can we have fiction? Yes. So it can get a little confusing when using these truth tables because sometimes you have to move backwards. So even though this implication is moving from left to right, when we're reading the table, we're going, this implies that, this implies that, this implies that. So we're comparing this column and that column, but in that direction. Okay, so this is a multifaceted problem. We have to take the statement and translate it into symbols, and then write down a truth table and figure out all the various combinations of the truth values for the individual simple statements, and then build up the truth values for the more complex statements. The trick to make this take up less space is to use these sort of implied columns. So kind of give the individual symbols their own columns. Then the or gets its column and the implication gets its own column. All right. So, very important. The implication, the conditional, is a directional, is a directional connective. It has it does not, it's a one-way street, that's what I should say. So P implies Q is not equal to Q implies P. These are not equivalent statements. Okay, so we can't, it's not commutative. We can't flip it around. Let's look at an easy example. So let's let P be the statement, the truck carries ice cream, and Q, the statement, the truck is refrigerated. And if we build a truth table for this one, we can see how P implies Q and Q implies P are not equivalent. Okay, so P will do 2 trues and 2 falses. And then for Q, we'll do true, false, true, false. And now we will write down the truth values. So again, fact within fact, yes. Fiction within, my color's ready. All right, fiction within fact, nope. Fact within fiction, yes. Fiction within fiction, yes. Whoops. All right, and now let's flip it around. Now we're doing Q implies P. So now I do my fact and fiction in the other direction. So fact within fact, excuse me, yes. So fact within fact, yes. Fact within fiction, yes. Fiction within fact, no. Fiction within fiction, yes. So here we can see that the result of the 2 columns is not the same. We have different truth values for P implies Q and Q implies P. They are not equivalent. Okay, so now we know they're not equivalent. What happens when we put them together? Then we get something called the biconditional. So bi meaning going in both directions. The conditional P implies Q and Q implies P. We call this the biconditional, and we write it down as P if and only if Q. So that's how we read the double arrow. Okay, that is not mentioned. Let me write it here. So the biconditional, which is the double arrow, should be read if and only if. P if and only if Q. Okay, so we can put 2 conditionals together and build a more rigorous logical statement, which is the biconditional. So let's look at the values here. So true, false, false, true, false, true, false. Okay, so like I said, with these more complex statements, the way to consolidate the table is to kind of give the symbols themselves their own imaginary column. So the and symbol will kind of get its own column, and we'll populate that with truth values once we figure out the truth values for the individual conditionals. All right, well, we just did this up here, so we can copy that down directly. So that was true, 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 and then true, true, true. And we had a false here and a false there. Okay, so those imaginary columns take care of the two conditionals. Now in this middle column, we'll get the ultimate result for the and. So remember, with ands, all you need is one false and the whole thing is false. So true and true, right? True and true gives us true. False and true gives us false. True and false gives us false. True and true gives us true. All right, so this middle column, this is actually the ultimate result. This is what we want. Those are the truth values for the biconditional. So if we instead had made a column for the biconditional, P if and only if Q, then its truth values would be true, true, false, false. Coming directly from here. So these are equivalent statements. Biconditionals. Okay, so something that we need to talk about before we can proceed to doing more complicated logical statements is establishing what we call the order of precedence. So we don't want there to be any ambiguity when we write down these more complex statements with all these various connectives. And often the way we avoid that ambiguity is we use parentheses, but a lot of parentheses can make the statement kind of over encumber the statement with lots of symbols. So instead of doing that, we establish an order of precedence. So that means as you're reading from left to right, a statement like not P or Q, you know whether or not this sort of statement means not P or Q, whether the parentheses go around the not P, or is it not P or Q? Do the parentheses go around the P or Q? Okay, so let's first just see that these two things are not equivalent. So we have P and we have Q. All right. And as I said before, we can kind of do imaginary columns here. So for the not P statement, I'll give it its own little imaginary column. And then for the and Q, it'll get its column. And then for the P and Q, it'll get its own column. And then the not will also get its column. So you can see the way of kind of consolidating the table here. Okay, so first let's do the not P column. So the not P column is just the opposite of the P column. So false, false, true, true. All right. Then we can do the or Q. So not P or Q. So we're comparing these two. Remember, for a or statement, all we need is one true and it's true. So we have true or false. So that's true. False or false is false. True or true is true. And then false or true is true. So that is the result column for the statement not P or Q. Okay, so now let's do this column. First, we do the what's inside the parentheses first. So P or Q. P or Q, remember, it's an or statement. So now we're comparing the P and the Q. And all we need is one true, and we got a true. So true or true gives us a true. True or false gives us a true. False or true gives us a true. And false or false gives us a false. Okay. So now once we have this column populated, now we just negate that column to get the result. So where whatever's true becomes false. So true, 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 we get false, 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 and then false becomes true. So this is the result column for the statement not P or Q. So we did this table to show that these two statements where the parentheses are around the not P versus around the or Q give us different truth values. These are not equivalent statements. So you can see that establishing an order of precedence is important. How are we supposed to read the statement not P or Q? Is it read this way or that way? Okay. So it'll turn out that the statement not P or Q should be read this way and not be read this way. Okay. So that comes from the order of precedence. So we have these 5 connectives, the negation, the and, the or, the conditional, and the biconditional. And the order of precedence tells us that when we're reading from left to right, the negation gets to highest precedence, then the and, then the or, then the conditional, then the biconditional. All right, so how does that work? Let me show you with this complex statement here. P and Q or R implies not S or R. Okay, so using the order of precedence, we find the negations first, and the negations take the highest precedence. So that negation is going to affect the S. Now, the ands take the highest precedence. So anywhere there's an and, it becomes the next layer. So I'm going to put green parentheses around that and. And then we get the or statement. So if there's an or, it becomes the, let me make these brackets. Right. So then the or statement gets its own set of brackets. And then finally the conditional, which we can see as one the outermost layer of this statement. So this shows you the order of precedence. Negation comes first, so it affects the S first. Then the ands come, so the ands connect these together. Then the ors, then the conditionals. And that all falls out from that order of precedence. So you can see this is a much more kind of overwrought way of writing down this statement. And it's much neater and more elegant to write it down without all these parentheses, but you have to be sure that you understand the order of precedence for the symbols. Okay. So last example, it's easy to, at this point, you're learning some logic, and it's easy enough to think, what the heck, this is the most useless garbage. How is this ever going to affect my life? Well, the truth is logic, formal logic, the way that we're learning it, mathematical logic, is a part of your everyday life, almost every living second, especially if you spend any time on your cell phone, which most of you spend almost all your time on your cell phones. Let's be real. So computer languages, that is programming languages, all are predicated on formal logic. You use formal logic directly when writing down computer programs, computer software. And we use the conditional statement, that is the implication, quite a bit in computer languages. So the form that it takes in computer languages is the if then else statement. And the idea here is that we can have a condition: if this, then this happens, and if this is false, then we do the other option. So we'll look at a simple example. This is a very simple program here. We want to determine the value of C. So the statement reads as this: if A times B plus 6 is greater than or equal to 10, then C is equal to A times B. Otherwise, if this condition fails, then C is equal to 10. So let's look at how this works. I'll give you two different value examples, two different values for A and B. Let's see what happens. So if A times B plus 6 is greater than or equal to 10. So let's determine the truth value of that statement. A times B, well, A is -2. B is -7. And then we're going to add 6 to that. So what is that equal to? That's 14 plus 6, which is 20. Is that, 14 plus 6, which is equal to 20. Is that greater than or equal to 10? Yes, it is greater than or equal to 10. So the if statement is true. So if it's true, then we set C equal to A times B. So then C is equal to A times B. So what is C equal to? It is equal to -2 times -7, which is +14. All right, let's look at another case. So what is A times B plus 6? That's equal to, in this case, -2 times 3 plus 6, which is -6 plus 6, which is equal to 0. And is that greater than or equal to 10? No. It fails the condition. So since it fails the condition, we do the else. So the else says that C is equal to 10. So that's a very simple way in which logic plays a role in your formal logic plays a direct role in your everyday life in computer programming languages, right? And this is a way in particular where the implication plays a role. Okay, so that is the conclusion of 11.3. Stay tuned for homework and your next lecture on Wednesday.